This one right here?
No, the parentheses.
Parentheses right there. Oh, that says and V.
Oh, okay.
Okay. The electric field out at infinity is 0. The potential out at infinity is 0. That's why we're choosing that point to start from. And then we go from 0 to wherever we want to find our potential. That's like counting from 0 to, R. Yes?
Where'd the x squared come from? Why is it squared?
Well, because the electric field is equal to 1 over 4 pi epsilon naught times q over r squared.
Oh.
And I'm just taking the x component of that, right? So it becomes an x squared. The further you head out in the x direction, the further this becomes going in the x direction. Okay. Any other questions about this? Yes?
What do you mean by like a chunk?
What's that?
Like you said that we should be able to find the potential between parallel plates, and then also you said like a chunk.
Oh, chunk. Maybe going from here to here
Okay.
instead of from infinity, right? Which essentially changes your limits. Okay. So the two things that could change, right? This right here. This is the equation we plugged in for E. That could change. The limits can change, something like that. But I pretty much am going to give you a problem where E and E and dx are in the same direction, or maybe perpendicular. In that case, this would be 0, right? So that's another thing that can happen. Okay. Now, the other equation, going in the other direction here on this this relationship, is this right here. E is equal to the minus gradient of V. Okay, well, what that actually means is E is equal to minus partial V partial x I hat minus partial V partial y j hat minus partial V partial z k hat. Okay. Now the book just says it more simply. They say E is equal to minus dv ds. So they just want you to do it in one direction at a time, but really it's the gradient, which means it has this, it's kind of the direction of the downward slope, right? Which is why the relationship between V and E is similar to that of a topographical map, right? And we'll get into that in 1 second. So this is the definition that the book uses. Which one do you want me to put on the equation sheet?
Middle one.
The middle one?
Yeah.
Both. All of them. You know, the more complicated the equation sheet is, does not necessarily mean it's a better equation sheet. Middle one. Middle one? All right. I like the middle one the best. Well, I like this top one, but the middle one is pretty good. Okay. Now, an example of this graphically would be like if you have some shape. Here's V, here's S, or whatever whatever the direction it is, and you can have several different types of shapes. You can have some parabolic shape. You can have some flat shape. You can have some curved shape like that. And then you need to go back and figure out what E is from there. Okay, so if we have some parabolic shape like that, that means, right, this is kind of like the relationship between position and velocity going in the other direction. So this is position, and now we need to figure out what the velocity is doing, only it's the negative of whatever the slope is here. So this is curving up like that. That means we're going to have some negative constant slope like that in our electric field. Anywhere where the potential is not changing, you have zero electric field like that. Okay? And then if we have some negative sloping line right there, that's going to be some positive constant electric field like that. So this would be the relationship between V and E in this direction. Okay? So just think of back to what you learned in 141, the relationship between position and velocity. We also learned about equipotential lines. Equipotential lines give us another relationship between V and E. Remember this right here. We had this in lab. If this is some V plus and this is some V minus, in other words, we're going down in voltage in that direction, there are 3 rules to live by. The first one was that E is going to be perpendicular to the equipotential lines. So if you pick some point right here, E has to be perpendicular to it, like that. That's what E is going to look like. The second thing is that E points in the direction of decreasing voltage. So in this case, here our potential is higher, here our potential is lower. So E is going to point in that direction. And if you pick some spot right here, it's always going to be pointing downhill. Okay, that's another way of saying that. Downhill. If you take the topology analogy seriously, that's the direction of downhill. And the third rule, what was the third rule? It's hardest to remember. That's right. If you take the spacing over here, that's delta S. E is inversely proportional to delta S. So over here, where we have a large spacing, that means that we're going to have some small electric field like this. And up here where we have close spacing between the equipotential lines, that indicates that we have a strong field. Other things to note about this is that positive charges create mountains or hills. And negative charges create holes. Okay, so a positive charge would have some equipotential lines around it like this, and they're going to be decreasing. So this will be like 100 volts, 50 volts, 25 volts, 10 volts. And that looks like a hill. If you put a positive charge anywhere on here, what's it going to do? It's going to roll down the hill, right? So it's going to have some force in that direction, causing it to roll down the hill. And that's the direction of the electric field. Likewise, if you put a negative charge here, it would be reversed. Maybe negative 100, negative 50, negative 25, negative 10, and the ball would want to roll down into that negative hole, something like that. I would look at the lab that we did regarding this stuff, drawing equipotential lines I would practice that, or at least look at that. Knowing all these relationships is important. And that is it for that part. And let's go ahead and take a 5-minute break.